So this afternoon, we have the pleasure of having Mao Châu Luo about nonabelian Fourier kernel and Lafforgue transform.
Thank you, Gary. So just before the talk, so Gary asked me how to pronounce my last name. And my answer is, Gary, I'm disappointed. This is the 5th time you asked me this. But to be fair, it's only the 3rd time. All right, so this is a joint work with Zhilin Luo. So I think I tell you today's video collaboration. So we give solution to this case, the development question program, the facility program. So we give a solution to one of the questions, and only particular case SL2 and GN2. So, but it's nice enough that I decided to tell you about this. But actually, the solution has not much to do with the problem itself. So I should try to review it very quickly so that you can come to the how the solution, spell out. So let me start with this. We call some element of the conjecture development question. So it's about how to approach to construct the functional equations and meromorphic continuation of automorphic L functions. So let G be reductive groups over global fin F. And F B going to be local fins. So later it will be local F going to be local later. Now let F be local. And you have to define automorphic L function. This.
Watch your back.
So we have a representation of the Langlands dual groups, and so with that, every time automorphic representation roughly if it has a product of representation of local groups, then we, following Langlands, you want to define the so-called automorphic L functions, SL, I, or rho, the central object in automorphic theories, and it's the Euler products that replace B and S pi B of rho. So here S is complex parameters, and rho is this representation of the dual groups. Well, this is this factor is modified for unramified place. You set up a transform. I'm not going to report that. And then the extraordinary conjecture that if we can justify for every single independent place locally independent because they are local component of automorphic forms, and then the whole thing had to have a meromorphic continuation. So it's this, the Euler only converge to S greater than something, and have the functional equation in the same way as a Riemann zeta function. All right, so the known case of this, like D is basically the principal in place, and rho and then LG is GLN, and this is identical. It's standard representations. So this is the for n1 to 1, this is A, is this, and for n greater than 1, this is both modes are K, and maybe come another one. So it's coming from this that this is basically can be formulated as a Fourier theory. So we have as Fourier theory have space of test functions. So this S space of short Bourrat functions FD. So given first function for given place and for it is going to be compact, globally constant function. And for the matrices, then we look at the space of the, for the matrices is the vector space into the same, right? This is the best functions. And then I'm doing it very fast and cannot go to any detail. Nonabelian transforms. You know, that is how to just watch how this function act on irreducible representation, and let that give you some idea on, and that is the L function. So the Melian transform of this space are basically the ideal generated by L functions. And so we have, but then what is responsible for the local functional equation, global functional equation is the Fourier transform. So you know that historically the Schwarz function itself is coming to birth because when Schwarz on the space that is stable by Fourier transform, so it's come together. And on this we also have the Fourier transforms, and so this gives you local functional equations and also the Poisson summation formula. That will give you the global functional equation. So there's it's just easy to remember that, you know, how you derive things in quite a lot of words. So I just want to leave the you know, that's what the core of my talk today is to remember that how you define the Fourier transforms of this space. So what, you know, this vector space, you need to do some choices. And here the choice is the kernel is the function psi of the trace. So psi is additive characters of your local fins, and trade the trader matrices. And here the transform is some Schwarz function, then you convolve this hash with this side of the trace and this solution H. So and this is to be interpreted as, you know, the empiric case at least, the real case also is as an element of stable Bernstein center, some kind of generalizations. All right, so so in general, Langlands propose if you know from Fourier it is conjectures, then you can just reduce everything to this case GLN, because you can transfer things into GLN, and that's it. But functionality is very far from being proven, and Bachmann and Kaplan propose some kind of opposite approach that you should prove this first, and then maybe to derive functorialities. And the way is, you know, just to try to guess what this should be for an arbitrary rho, arbitrary G. So, for example, for this space of matrices, and then there's something that you can, you know, can define some kind of monoid M rho. So this is not vector space anymore. It cannot add, but it can multiply. It's called monoid. So this is to the algebraic story, and it's well understood. You know, the space of Schwarz function is not known yet, but there's in Baberman, Besu-Karnikov, Finkenberg, and Carson have conjectures now what they should be. So at least we have an idea of what this space is. Also, we have the
conjectures only make sense for functional fields.
Well, I mean, if you generously interpreted, yes. And you can also make, you know, for this story, it's very important to have a basic function, right? You know, even to formulate the global Schwarz space, and for every place a one function, which is stable on the Fourier transform, 9 properties. And you understand at least the function Finke, what this basic function is. It's the IC of this more of the aspect of this monoid. It is in my joint work with Langlands and Boutier. So but one of the very peculiar things, what is this thing? So how do we define this? This is the kernel of the Fourier transform, dynamic transform, as an element of stable Bernstein centers, a bit generalized, but not much. So that it acts on, so this as Bernstein centers, it acts on every irreducible element by a scalar. And that scalar should be a gamma factors for every, so for G reductive periodic groups. And so Z and element in the Bernstein centers of G and F, then for every Bernstein centers is the algebras of invariant distribution, which is essentially compact. And so we convolve with some characteristics from the compact, we get a compact subpart, so we can act on vectors of smooth representations, which acts as scalar, right? So this is the, so we have this what I've written in gamma of Z pi. So we define a function on the set of irreducible representations, actually an algebraic function. And this had to be the Langlands gamma factors that appears in this local functional equation. So I'm not going to, because later we're going to define much later. So the question is how to construct an even Bernstein center so they act in a certain given way. Right? This is the questions. All right, so so what I just say is about this. All right, so I think it's actually quite a different problem because actually to construct has not so many element Bernstein centers concretely. So by our work somehow we now have kind of procedure to do that in a nice way. So I have in the Bernstein conjectures, we suppose to construct this kind of a geometric way. So I don't know that if a solution even essentially is geometric enough. But it's very analytic. It's just given by some integrals. So we construct this given by integrals. Complicated integral is really integral. I'm not sure that it qualifies as geometric yet. It's not, but it's uniform over Euro confines given type of bunch of integrals.
Will it make sense in our communities?
Yeah, it will most likely a geo case. Actually, it's kind of nice and geo case. All right, so first, the case is kind of, there is the obvious case is kind of G split torus. And so we have a rho and representation of the dual group of torus. So this is answer given by a bunch of characters, lambda 1, lambda d, t, and those are just characters from all characters of t. So this gives rise to some plenty right product of lambda I, a map from Gm V to T. So by writing T1, we add to product of lambda IGR. So we have homomorphism of torus. And here we have some kind of exponential function, that is exponential of sum of here. And in this case, so this is called the kernel of the Fourier transform denoted by J rho. J rho is given by just push forward this distribution. So here you need some regular relations, but it is not a big deal. So this exponential will sum. And the finite rate is Kosterman sums, and in periodic, so you need some regularization with a compact support, but this is fairly easy. And it works also even you can remove this, because when you have some Galois action here, but actually leave the Galois action on this set lambda 1 with that, and then make the state. So now let me try to explain you the way that I've been trying to allow to state at the beginning of this, and how I want to construct this. So, how to construct variable for the reductive group, right? So assuming for simplicity, assuming G to be so simple and simply connected. All right, so so in this case we have this. We look at so let's try to do it very naively. So this is as a function, and it must be a stably invariant function. So it just depends on the characteristic polynomial. So let me write this. Let me have this quotient, invariant quotient of G by itself. This is a phi space. This is not basically standard. So it's come by maybe some misnomer in my paper, the Langlands function to call this standard Hitchin base. It's nothing to Hitchin, but let's just come that way. So then this is a phi space, right? And for every torus, for a maximum torus, split or not, P alpha G. Then you have the map from P alpha to P alpha to C, right? If it's split, it's just a quotient by the variable. It's not split, it's kind of similar, right? So we have so here you have let's look at we have to look very much on the F1. So now F is local field. So it's mostly periodic, but what we do actually work over real very well. So now we have this map of P alpha F to C of F. And here the action is the group W alpha, which is normalized divided by the power itself. It's not the F1 of W, but really this kind of nicely. This happening the fibers. So on the torus, we actually have this function. We have this function J. We have this function J of rho of T alpha on T alpha F over C star C. And you know that actually W alpha invariant. Right. So we can just naively to descend it to here. So we can descend it to a function mu alpha of this. Now it's going to be a function on the image of this. Okay? This is not algebra, just image the torus in the conjugacy classes that have intersection with the torus of the image of this P alpha into C star. Well, now you see on your omega C of F is a union over alpha of this image. So think about the real case SL2. This by issue of phi line, and the torus is a split or compact. So it's compact, it's going to be -2 to 2, the choice map. And not compact is the remaining thing. That's the only thing we have to remember this. This is very important on the this -2 and 2. We have a function here and have a function here. And this one is the whole thing, right? So of course the most simple matter, why you don't check the sum of them, right? Well, there's some kind of thing with the intersection, but that is kind of measure 0, it doesn't matter for what you do. The sum of mu alpha. So it kind of tempting because it works in the principal case. With the principal case, just beside the choice and add to whether it's beside the choice. So this works for this naive kernel works for the GLN and the lowest standard. We divide exactly to the Boltzmann case kernels. But it doesn't work on neither any case other case. So it doesn't work. So this is one of the, this was realized by Laurent Lafforgue. That's why we have this Lafforgue transformators. So I think Laurent was trying to do but the same thing, then he realized that this does not work. It doesn't work with a principal series. So the sum of the J9, even sum of V1 for J1 does not give rise to the correct gamma factor of the principal series.
Yeah, I think what does it mean? Because you have to choose those J, what they call JLT alpha.
Yes.
So I mean, you didn't say anything about how you choose them. So by saying that for any choice that you cannot choose them, so this looks like so far you have like infinite freedom. You can choose those things.
No, I have for every torus have canonical choice.
I'm sorry?
For every torus have canonical kernel. The torus is
but you didn't describe it.
I didn't describe it.
Oh, okay.
All right, so what he does for G equal SN2 is something very bizarre. So it took me a lot of time to understand this. So you look at G naive. You look at G naive for SN2. So G naive as a function of the trace values. And it doesn't have a principal series the way that we wanted to act. So we had to do, to make it suffer with some operations. And what we do is the following. So we do the Fourier transforms of these things. So this requires serious thing. It doesn't converge nicely, but you have to work very hard to make everything converge. And then you have to divide by the absolute values of the dual variables. And then do Fourier transform back. So this is like the Lafforgue transformation in this case. And he claimed that this thing is going to act on principal series the way we want it to act. So the first question is, what the hell is this, right?
Yeah. So which row is this one?
Sorry?
Which representation row is that?
Any row. No, here's any row.
So it's the same transformation.
Yeah, so maybe let me formulate it a bit more better. So now we actually can forget about row. For every alpha, I just write a function on this, on T alpha, right? And I just descend it to the trace variables, and I take the sum, right? And so the question is now, can I write an element J in the stable Bernstein center so that it descends to the J alpha for every torus?
Right, J alpha is also non-trivial, right?
It just define this gamma action. Yeah, but yeah.
Man, we probably know how to do it, but I don't.
All right, so this is actually the question. I assume that this J alpha on tori, right? So you want the Langlands Bernstein center to descend to the J alpha, right? And that is the ideal question we are going to solve the first now. So in this case, the naive kernel going not to descend to the J0, let's call the rest split torus. But this one goes into the center of this G. But the question is, that is one going to be sent to other J alpha? Yeah, that's the answer is, it works for the symmetry square, but no further. So this is not the correct answer for. So even this bizarre thing, it works for the principal case, it works for symmetry square, but doesn't work for symmetric cube. So you need to do something else. So you need to see more. So really what this thing means to understand to solve this problem. Right?
Sorry, I want to see descent. What does that mean?
I go to descent. So now I'm going to to say a bit about more theoretical, explain what is the kind of theoretical framework of this, because all this is now kind of formulating in this not very rigorous way. All right, so let me recall something about the Bernstein center. So by the way, everything we do up the everything is completely rigorous for SN2, even for you and you know how to define it, but for other group, much more work to be done. But for this, everything makes sense, even the conversion and so on. So Z is this Bernstein center is essentially compact. Compact invariant distribution. Right. And so also with the same as algebraic function of the Bernstein varieties. No, so the irreducible representation up to inertial equivalence will give algebraic structures on that. And this thing have equally component, and it's kind of nice, but this sub-algebra, quite ideal, this non-linear algebra. So Z fin is the Z is supported by finite demanding component of omega. And this is kind of you work with it. We have analytic formula for this because it's by Moy and Tadic. You can prove that if Z is in Z3, then you can write Z as a local integrable function. And Z is J to G, and J is a local integrable function. Invariant. All right, and inside Z you have this stable of Z, the stable Bernstein centers. So this is a sub-algebra, so I'm going to define later. But this is can prove this is sub-algebra for SN2. And SN2, SN2 of course, but this is the same. All right. And so if we intersect ZST and ZT, then your distribution is going to be J dg and going to be a pullback of a function of a trace variable. And this function is going to be stably invariant, only depend on characteristic polynomials, this function of the trace variable. So now JC is a function of the standard symbols. So for this guy in both stable and finite. So we want to do a lot of this kind of function. And we require work to even trade variable to define analytic property for this. For example, they are going to be complete integrable function, for example. All right. So this is JC, and you can define the J hat C of the Fourier transforms for the integrable. All right, so now the next ingredient is the cocenters that have been mentioned in Roman's talk, in different perspectives. So we have this. Let me recall a bit about the normalization. Of stable or not, orbital table, and the cocenter. Right, so this system, when if you have worked with orbital to the normalization of orbital, it's a nasty business, right? But now I think I probably believe that we do have good normalization now, right? So this is for stable one that was in the one in paper with Langlands, so something normalizations. So we have it mapped from G from some simple simply connected group at least. You see, which is a phi space, right? Given by the choice of fundamental representations, right? And you have the, away from discriminant, we have the prime is the complement of the discriminant divisor by discriminant divisors, and the fibers conjugacy classes. All right, so because this is the phi space, we have a nice measure, just an additive measure. Right? Let's just think that region S from now is down 2. This is A1. So we choose a dx. And so apparently this looks very bizarre. Why should you take an additive measure? But it makes sense when you look at the torus. Right? You have this T alpha you see torus, right? And then you take the distance from P alpha, and then you just pull back the P alpha star. So let's say top form dx. And you can draw also the canonical top form of this. There is a form divided to a sum to choose the base of your characters. And write then this kind of the top form of the alpha. So this is what is up to a sum. And then the difference is going to be some function delta. Or what this is not going to be W invariant, but this is up to a psi, right? So the absolute value is 1 on the base. This is the square root of the fine scheme. So I write actually and in the SM2, this is somewhere S square minus 4 in this picture. This is all right. So rather with this, the way you define open is actually in the most simple way possible. You have H is your algebra of function or measure if you want, scope of support. And so we have, let's call this thing C, this map C. Then you are going to have push more, just push forward. This is a measure with compact support, so we have the right to push it forward. We get a measure with compact support on C. Then you're going to write this formula. So we define as your stable open integral on H is a push-forward measure, and to normalize correctly the measurement, standard measure. That's it. And so all right, so and I can do the same for open integrals. Why? Because the space of that this line, that this is possibly connected place to remove a singular point, exactly the set of stable conjugacy classes, right? But the set of conjugacy class, for example, from compact and have 2 elements, something like this. So a set of conjugacy class is so true. I have these pictures, right? You have on hyperbolic you have one single point, but here you have 2 points for every traces. So this is not algebraic variety at all, but it have analytic structures. You can just put it back from the lab. Right? We can put it back to the lab, so we have a canonical measure on this. You can decide which point I have measured zero, so you don't care about them. So you have a measure on this, put it back on this. So then you have if you have this map, let's go to the map to the conjugacy class is D. Then you can write the formula this class HDG. It's over the table of H of D, whatever it is, the measure we define by this one. That's it. And actually, this is actually not new. And you check thing, it's exactly the Harrison normalization. So Harrison normalization, you have this f of z minus 1 ex dg dt, and you have to put this delta, the square root of y discriminant. If you don't put them, you're not going to be bounded. So we have to put this delta to make it bounded. Right? So this is exactly this normalization. But in Harrison, he doesn't normalize dt. You just choose some dt. When the dt is going to be the pullback that define this formula. So we have an integration dt coming from the top form of the standard Hitchin base. So that is the story. I think it's not complicated. So this is the thing, and but this kind of analytic story, you can define what is O of H or as O of H. But there's a kind of algebraic side of it. You can also bypass down. You know that the space of O of H is the same as the cocenter. Two functions have the same homotagons, even if they are commutators, different commutators. So this is exactly this, right? And also, and then you can just define what is the stable cocenters. So like you will see, if you look like in Roman, and then the C stable, I just define it to be the S4. So that's where all stable augmented cotagons, right? So now, what is this nice thing about this is, this space have two structures. Right? It have here up by the Bernstein centers up on this. So the center of the cocenter as always. So it stabilizes the commutators. Up on this. So we define the Z stable. So it up on here. So let's just say that the kernel of the have this map A to this, and the I stable to be the kernel of this map. You should define the Z stable to be the element of the Bernstein center so that up stabilizes. And somehow this is just a kind of preformative usual definition. And the conjecture is that this thing is algebra. And it works in this SL2. We know enough SL2 to easily to prove that this thing works. All right, so we have two things. We have this kind of S4 of H, and a structure of DST modules. It also has the kind of structures of modules over the algebra of functions. And I'm not precise on this on the standard Hitchin base because they are functional. Standard Hitchin base can multiply by a function, maybe I can impose some condition. But they have two structures. So somehow it's not only about this, but one of the things is, this here algebraically kind of poses. If you have a neighbor in stable Bernstein center, you can multiply the neighbor in the stable cocenters. But the question is how you can write as integrals. So the question is how to write the multiplication of ZST on a CST with integrals. Right? Well, after all, if you look at the finite element, they represent some function on the trace variable. So this is another function trace variable. So they multiply together, they need to have some kind of complicated table to write the multiplication. So that we're going to find out what the formula is. Right? All right, so this is So again, it's just any questions so far? I think it's just a kind of conceptual point. It's not that hard, but it's really important to nail it down that you have to normalize in this way, just these push-word measures, and they happen to be essentially Harris-Schaller normalization. And it's most nicely. For example, for this definition, you can prove that this from this. So it obviously is most on the regular semi-simple locus, but actually continuous. This guy very deep analytic fact that this function is continuous. And for SN2, we can compute it, but in the case of, by the form, you can actually prove it. It's some kind of more perception. But anyway, I'm not going to go into this stuff.
Okay, but you said that there are some sign benefits.
No, here is no sign. It's really continuous, but it's not smooth. All right, so now let's go back to Sasha's question about this descent. So you really have descent map because for G equal to SL2. And now we have exclusive in this case. So we have 4 tori. So for residual characteristic not 1 to 2, as I have 6 or 8. So alpha is 0, 1, 1 plus minus 1/2. So this is split. This is unramified and 2 unramified torus. Right? For real, they have only 2 torus, R and C. And so the T alpha is a torus, so it's like one just not one element in the these quadratic extensions. And you have contour lifting that you know in this case. Lifting a representation from a torus to SL2, packet SL2. And that gives you like this same class from the ZST. You can decrease only by packets, so just have that from ZST into the ZST of T alpha, but this is torus. It's just the height curve algebra of the torus. And that we have to be stable by tau alpha. Tau alpha is the value of calculation. So this is sender. And this is a homo algebra.
It's a map from where to where? It's a map from the stable center to
into the stable center of the torus. It just gives you the formal map from the packet. You have the map from the packet of torus lift into the packet of SL2.
Oh, okay. So
you're
using the lifting. So
everything lifting. So this is a descent map, but they also another important structures is the Langlands cable transfer map. So this is very important paper, but I don't see I've maybe among 1 or 2 people who have to read it. So the singularity transfer. He defined, computed explicitly this. So that is going from the C stable to H stable. So this is algebra, the homosome algebra. This is one of modules. But let's say so his reason is you have map from packets, then I must have map from mapping character to stable characters. So dually you have map from the stable cocenter to stable cocenters. This is the map. And just put together after what is very nice to need to remember. And it was not absent in Langlands paper. This is actually algebra model. So this people call lifting rho alpha. This T alpha, the T alpha is rho alpha unit. So that is very important for calculation to realize this. So the map on algebra is Homer algebra. This is map on modules, and this is compatible. It's linear. And that's very curiously, Langlands wrote paper. You compute up to a side, very careful, but he doesn't know that this map has a formula. This map had a formula from 1963 in paper of Gelfand-Graev. So that's why you can write a lot of formula, because you can write the formula for the stable transfer.
Because one can just write in the character of this list.
Exactly. But this map is just the adjoint map to the same
Yeah,
kernel.
you just if you do Mellin transform aspect.
No, you don't have to do Mellin if you want, but this map of characters is dual to the map on the cocenter. And the dual to the transpose matrix, so it's exactly the same formula. So I don't think that I have it. I would love to write the original formula of Gelfand-Graev, but I don't have the time. But I just write it the way that I like here, right? If you start with the function f in CSP, stable, now we have just some S4 function. So it's from one variable, right? And then you want to write a function on the torus. What you do with this thing, you want to do the Fourier transforms of f and the Fourier transform back. And in between the k, you want to multiply by the quadratic characters associated with the quadratic extension. Right? And there's just some kind of slight annoying thing that you put the lambda factor. This is the form of the building, right? This is the lambda factor. So it's essentially this the Fourier effect of the multiplication by the quadratic characters correspond to quadratic extension. It's the answer. And so we start with a function on the trace variable. You do this and get another function, and then you just do the Pn plus stuff. So that's the torus. And this is the. So in the original formula, Gelfand-Graev write this as additive convolutions. If you look at formula, it's additive convolution. And you look at additive convolution, with the Fourier transform multiplied by characters.
So what is lambda?
Lambda is a very constant. Yes.
Constant.
It's a constant. Yeah. All right. So you see that. So now I can come back to the Lafforgue story. So there's Lafforgue in both sets. You have a map from Lafforgue from the map of Bernstein centers into the cocenters. And you have the Lafforgue inverse, and not inverse, but variants in the other direction. So we have a map, this on the kind of Z linear map. So the idea is this: you start with an element in the Bernstein centers, right? So on every irreducible rectangle, it acts by some scalar. It's just one associated number of cocenters, so that the trace of that element is the same scalar. So here the trace. Let me write the formula. So we want to that. So Z in here and F in here. So we want to have this formula. The scalar on psi to the trace of F on psi. So that is a formula that we want to do, right? So this doesn't normally works. It works, for example, when some element, some inertial class have the induced representation may be reducible in some kind of troubles. But to remove them, just remove those guys, and it remains some kind of open subset of the Bernstein varieties, maybe some variety classified irreducible representation, they're isomorphism. So this can make sense over this. And then you could just extend whatever you can, right? And they have merit on both directions. So now so you have this map on both directions. And the thing is that I want to say that you can restrict. When you restrict the thing to the stable part, it has a formula. And for example, this you have the Lafforgue of Z is a formula that I wrote that is Fourier transform of psi minus 1 of Z divided by absolute value. And the Lafforgue prime of F is the same when you multiply with So this operation of Lafforgue actually has a very neat representative theoretic that should map it from the center to the cosine on the stable part. Right? That's what it does. Actually, you cannot prove it. So you can prove it, but indirectly. But what you prove is that if you map the ZST to CST, so this is Lafforgue map, and then you map the transfer map T alpha to the torus, and then this is a descendant. This is different, and the rho alpha is what you expect. Rho alpha would be Fourier transform multiply with the quadratic character divided by the absolute values in its first form back. And you can prove this by calculation. Unfortunately, you just calculate bravely what it does by using Fourier representation. You can compute it. It kind of, especially convergence, is kind of suffer a lot to prove the thing we do have to converge. So you can prove this formula, and so you can derive Lafforgue is what you write and so on. So this gives rise to at least for the questions that you can have a formula to be set. So in another theorem, it's so now I look at this, the sum of this rho alpha. So alpha can be 0, 1, plus or minus 1/2 from VSP to the direct sum of T alpha, tau alpha. So we have a formula for each of them. Again, Fourier transform multiply with quadratic character divided by first form back. This crazy formula, but it's actually a home of your algebras. You cannot explain why it is, but it is the case. And now you want to, in what sense, you can inverse this? How can inverse this? So this is actually, you can put this inject. Now, because you know so well the SN2, you can draw the pictures with the, let me draw this. So we have this is the split component. Just roughly there's a square, a circle. And then you have the diagonal representation coming from the unramified extension. So it's going to be something like this. Okay. And you have something, two ramified extensions. They intersect one point. That is actually one of the miracle of the Langlands corresponding to this point. With this packet of 4 elements where the 3 series intersect. Let me do this point. There is one line like this. With another line, another torus going like this. It had to suppose intersect at the same point. Like this, right? And then there is a standard representation. Stick out in somewhere here. So this kind of picture of how the SL2 is. Right? If I'm correct. All right. Anyway, I'm correct. So this is the. So when you look at the Z standard, you remove the standard doesn't going to do anything anymore. This standard only appears on the cocenter. But this map is injective, right? This is kind of normalization. We just define by the function has to take the same values here with 2 components, etc. So this can describe the image. For example, the values, for the trivial characters of the unramified torus is correspond to the principal series. And you want that the values of the function J alpha on the unramified torus as the trivial characters coincide with the trace of the value on the principal series at that principal series. You have bunches of operation like that. And the most difficult one, you actually deal with the one that is the share point of 3 series. That is a supercustodial package with 4 elements. And the way you divide by 2 by 2s, there's 3 ways, and that corresponds to 2 series. It's just really extraordinary how it works out. Anyway, and then you can just staring at this picture, you can describe the image of this map where they intersect, and you can write integral formula for the inversions. Because you have a canonical decomposition of the cocenter as a Russian stable modulus, and with projections given by integral formula. I don't think I have time to elaborate this point, but for example, this it's rather nice modules, right? It's kind of nasty when you look at the function over the trace line, but as module over Bernstein center, actually kind of very nice. It just have this point when we remove the standard, it becomes a free module rank 1, right? That is what it is. And now, for example, you can decompose. You can have the piece that is supported by the circle. It has a piece supported by the part of the line here, 0 dimension, and this part, right? So every part you have just direct factors. The question is, you have these direct factors as Haeckel modules. How do you write projection integral from of the trace variable? So what you added happened because you have this map on the cocenter. This map is given by this very nice transform, this Gelfand-Graev transform. So you invert the Gelfand-Graev transform. But this, if you remove this, the Gelfand-Graev is actually involutive. But the thing that this is not what you do. That is the subtle thing. Although they tell me that this is involutive, it's not working that way. You want something that is because this should supposed to have nothing to do with principal series, have 0 trace of principal series. So whatever you do had to be function which is concentrated on the elliptic locus. Right? So it's very close. It's going to be normalized elliptic trace of this formula. So there is some delta factors and then elliptic, and that is the formula that use that to do the inversion. Stop here. Thank you.
Any questions?
We expect to have
this theorem is still for SL2.
SL2 from GN2. Yes.
junction for Gelfand.
Well, I mean, I firmly believe that every piece of this should be worked, and it should have for other groups. But I don't know how to draw these pictures for. But for sure.
You have an idea of what should analyze Fourier transform trace variable?
No, but I have an idea what the Lafforgue transform is for GLN. What is the Lafforgue transform is for GLN? You have a very complicated formula because at the beginning we just try to understand this thing, how this act on principal series. So we just take the pen on hand, just try some trace variable function, let it act on principal series. It's horrendous calculation, but at the end you get a nice formula. And you get some kind of polynomials. It's not as nice as just absolute values, but it's something that look nice. But although it look nice, I don't know how to to interpolate it for other groups.
I don't know how to write J alphas for other groups.
Yeah, I don't know, in the Gelfand, I don't have Gelfand-Graev for other group.
Yeah, it's equivalent to writing character of the lifting from a torus, and I think nobody knows how to do it in GL3.
You do have formula, but it look very ugly, but it's not
Is there a
nice.
formula?
There is, you know, that, you know, you can call it formula or not, but there is a formula, factor formula. When it, so on this formula is so nice, Fourier transform and multiply by the most simple method you can do because quadratic characters, and you do multiply with the quadratic characters. But yeah, what is the story for other group? But I think it cannot be, you know, for the Lafforgue transform, I'm pretty sure that there's a formula.
Is there any version of like shift theoretic version of these constructions?
Well, I mean, we have people there we know more, but I don't know, yeah, but there's something that is really well, I think one David Kasdan told me that there must be some kind of business extension that what you know on the a function on the hyperbolic trace and extend it. And I just didn't know how much sense of what he said. And it happened to be true here. That is kind of something that extraordinary in this. You can let me just write the formula here. Well, it take 1 minute. Okay, here you can write as for h. There is something that called the delta standard elliptic, maybe delta. There's something that you do with energy character of the standard, like the delta function here. Then there's the piece from the shape E naught tau 0, and then there's several similar pieces for the four polarizers. So for these three pieces of the octagonal decompositions, with a empty character formula. But I think the most important piece is this one. So this one is, this map is a lifting from a function on the hyperbolic trace. It will just extend canonically on the other traces, and they exist. And for example, if you plug in a spherical function, and this map can calculate the state of the integral function. I've been doing that for 30 years, but I never realized actually there's a formula for this. There's a formula for stable operable of every spherical function. It's complicated formula, and so this may correspond to what we call this kind of intermediate extension from the hyperbolic trace. But I don't know, but this is.
Any more questions? Thank Châu again.